So the objective of this topic or this week is at the end of the lesson, the learner will be able to 1. Define computer interconnection structures. 2. Describe the bus interconnection. 3. Know the 3 types of bus structure. 4. Define the PCI. Now, program concept. So hardware systems are inflexible. General purpose hardware can do different tasks given correct control signals. Instead of rewiring, supply a new set of control signals. So what is a program? So a program is a sequence of steps. Okay? So it is an arithmetic or logical operation is done. So for operation, a different set of control signals is needed. So function of a control unit, okay? So for each operation, a unique code is provided, like for example, add or move. So it's the, actually this is a code for example, you're going to code an assembly language, you can use these codes, okay? Next, a hardware segment accepts the code and issues the control signals. So computer interconnection structures or the components, we have the processor, we have the I/O module, and we have the memory. Processor, the control unit, and the ALU or the arithmetic logic unit constitute the central processing unit. So meaning to say the processor or the CPU composes of the ALU and control unit. Okay? Then the I/O module, this is the data and instructions need to get into the system and results out. So this is what you call the input or output. So memory, temporary storage of code and results is needed. So this is the main memory. So this is the computer components with the top level view. So as mentioned from the last topic, if you remember, we have the CPU, we have the main memory, and we have the I/O module. The components of the CPU, we have the PC, or also known as the program counter. We have the IR, also known as the instruction register. We also have the MAR, or also known as the memory address register. We also have the MBR, or also known as the memory buffer register. Okay? We also have the IOAR. We have the input-output address register. Okay? And then we have the IOBR. We have the input-output buffer register. And also, from the CPU, we have the execution unit. So again, the components of the CPU inside, we have the PC, the MAR, we have the IR, we have the MBR, we have the IOARBR, and we have the execution unit. Okay, so we also have the IO module or the input-output module. So this is the IO module which contains the buffers. And aside from that, of course, we have the memory or the main memory. So the contents of the main memory are what? The instruction and the data. Okay, so again, these are the components. So let's talk about the instruction. So we're talking about this part under the main memory. So under the main memory, as I mentioned a while ago, so we have instruction and data. So let's discuss the instruction cycle. In the instruction cycle, there are 2 steps. We have the fetch and execute. So how does it work? How does the instruction cycle work? So from the start, we are going to fetch the instruction. So after fetching the instruction, you are going to execute the given instruction. Okay? So next, execute the cycle, okay? And then again, you're going to fetch the next instruction. So as we all know, instructions are step by step. So you have to do it also step by step. So fetch the next instruction, execute the next instruction, and then if you're done, halt or temporarily stop. So fetch cycle. Program counter or PC holds the address of next instruction to fetch. So again, the PC or the program counter holds the address of the next instruction. The processor fetches instruction from memory location pointed to by PC or the program counter. Now, increment program counter unless told otherwise. So, instruction loaded into instruction register. And the processor interprets the instruction and performs required actions. So, that's how the fetch cycle works. Next is execute. After fetching, try to execute. So execute cycle, you have the processor memory wherein the data transfer between CPU and main memory. The processor I/O or the processor input-output, the data transfer between the CPU and the I/O module. Okay? And then the data processing, some ALU and logical operation on data. Next is control. This is the alteration of sequence of operations. And the next combination of above. So this is the execute cycle. So processor memory and then processor I/O. Next is data processing. Next is control. The next is the combination of all. So this is the sample of a program execution. Okay? So for example, from here, we have the, from the step 1, we have this memory, and this will be passed into a CPU register, which is this one. Okay? Step 1. Next is step 2. From step 2, okay, we're going to pass this one, and then we'll record in the CPU register. So you're done with the memory 300. Moving on to the next memory, which is 301. Okay? The 51941 from memory will be passed into the CPU register, which is the IR here. Okay? Passing this record. Okay? Next is step 4. So since you're done with the 940, we're going to move on to the next memory, which is 941. You are going to move this one, okay, into this. Now, if you remember, the first record of the CPU register is 3. Okay, that's why we have 3 here. And then the memory pass a 2 value. That's why we have plus 2 here. So 3 plus 2 is equals to 5. That's why we have 0005 here at the CPU register. Okay, next. Okay, I have here the third one. So we're done with the 301 memory. Moving on to the next one, which is 302. We have this one from the memory, which is 2941. We're going to pass that into IR. So the new stored in the CPU register is the 2941. Step 5. Step 6. Okay, now the memory here from the AC is 005. Since the last part of the memory here is 941, you are to pass the output or the result from the CPU register, which is 0005. So that's why from step 6, the memory in 941 is 005. So this is an example of program execution. Okay? So instruction cycle state diagram, we have a diagram here. So you have the instruction fetch. Next is you are going to instruction operation decoding, operand address calculation. So fetch the operand. Next is if you have multiple operands, so data operation, operand address calculation, and then operand store. Once it is stored, okay, what's the next step? Return for string or vector data, okay? So going back, as this is a cycle, if the instruction is complete, then fetch the next instruction. Okay, that's why you're going back here. So this is a sample of the instruction cycle state diagram. So interrupts. So remember our topic last meeting is about interrupts. So just a recap. mechanism by which other modules may interrupt normal sequence of processing. So program, we have overflow or division by zero. So timer, generated by internal processor timer, and also used in preemptive multitasking. So input-output from I/O controller. Okay? So we also have the hardware failure. Okay, so this is an example of the program flow control. Okay, so we have here three types. We have the letter A, no interrupts. Okay, we have no interrupts. We have B, interrupts, short I/O wait, and we have D, interrupts with long I/O wait. So from here, user program, write, and then write. After writing the code or writing the program, so you have the input output and then you have the command and then end. If there is no interrupts. What if there is an interrupt? Okay, so this is a short input output. The user program will write again, write of course. And then next, the IO program, checking the IO command. Okay, so in case if after writing, there is an interrupt handler, and then next, you can end. Okay? So this one is the long interrupt. So user program, write the program, write, and then write. So IO program, so IO command. So after writing again, there is an interrupt handler. So after interrupt handler, write again. And then after that, check again, write. And then next, check again the interrupt handler, and then end. So this is the sample of program flow control with no interrupts, with short I/O wait with interrupts, and the long I/O wait with interrupts. So interrupt cycle. So added to instruction cycle, processor checks for interrupt indicated by an interrupt signal. If no interrupt, fetch the next instruction. So unless there is an interrupt, suspend the execution of current program, save context, set PC to start address of interrupt handler routine, process interrupt, restore context, and continue an interrupted program. It's the same class if you are, for example, you are doing your program, okay? Assuming that you are coding. And then, while coding your program or while writing your program, you are always testing your program, right? That if it executes correctly, is the correct instructions correct, okay? And then there are times that after running while running your programs encounter some errors, okay? And then having that errors, you have your program interrupted. So of course, if your program is interrupted, you have to recode. What is the error? What is the bug? I have to code it again. I have to write the correct code and then test it again. Okay? So next is transfer of control via interrupts. So example that interrupt occurs here. So for example, we have the implementation here, I plus 1. So we are testing the I plus 1, the implementation here, and then will be passed into an interrupt handler. Okay? So this is the transfer of control via interrupt. So we have the user program and the interrupt handler. So next is instruction cycle with interrupts. So this is again start, fetch the instruction, execute the instruction. So if interrupts are enabled, check the interrupt and then process the interrupt. So interrupt cycle, execute the cycle, fetch the cycle. So next, fetch the next instruction, execute the instruction, interrupt is disabled. Okay, so no interrupts. Fetch the next instruction, execute the instruction. So next is halt or temporarily stop. So this is the instruction cycle with interrupts. So program timing, short I/O wait. So this is the diagram. So for example, we have the time here. So processor wait, I/O operation. Okay, so this is without interrupts. So this one is from the right side of your screen is the I operation with interrupts. Okay, the 2A here, the 3A here shows the interrupts. This is the program timing with long I/O wait. So without interrupts and with interrupts. So it shows how the CPU works inside. Okay, while doing your you have your program and then there is an interrupt, what happens visually? Okay, so next is the instruction cycle with interrupts state diagram. So you have here the instruction fetch. Okay, we're going to start here, and then operation decoding. Next is operand address calculation, operand fetch, data operation, operand address calculation, operand store. Next is what? Interrupt check. If there is an interrupt, okay. Or if there is no interrupt, go here. Next is what? Return for string or vector data. Okay, either you're going back to this one to operand, and then if not, go here, this straight instruction complete, fetch the next instruction, and then instruction address calculation, and fetch the next instruction. So this is a cycle. So multiple interrupts. Disable interrupts, processor will ignore further interrupts while processing one interrupt. So interrupt remain pending and are checked after first interrupt has been processed. Interrupts handled in sequence as they occur. So define priorities. Low priority interrupts can be interrupted by higher priority interrupts. When higher priority interrupt has been processed, processor returns to previous interrupt. So this is the multiple interrupt sequential. You have the user program here. You have the interrupt handler X, and you have the interrupt handler Y. So again, showing you visually how does it handle interrupt sequentially. So this one is a nested interrupt. So we have the user program, we have the interrupt handler X, and we have the interrupt handler Y. So time sequence of multiple interrupts. So you have the user program here. So timer is equals to 0, okay? So if equals to 10, so printer ISR, okay? And then T is equals to 15, communication, okay? So T is equals to 25, so this ISR. So this is just a visualization of time sequence of multiple interrupts. Connecting. All the units must be connected. Different type of connection for different type of memory. So again, we have the memory, we have the input-output, and we have the CPU. So computer modules. For the computer modules, we have the memory, we have the I/O module, and we have the CPU. So these are the modules or the components. The memory can read and write. So of course, it stores the address and the data, and of course, it will store it here in the memory and will give an output of the data. So I/O module is able to read and write. Okay, it has the address, internal data, and external data. And of course, it will provide the internal data as the result in external data and interrupt signals. While the CPU handles instructions, handles data, handles interrupt signals. And of course, the CPU will provide or process the address, the control signals, and the data. Next is the memory connection. So again, memory receives and sends data, receives addresses, receives control signals. So when you say control signals, we're talking about the read, write, and timing. So input-output connections, this is similar to a memory from computer's viewpoint. So output, receive data from computer or send data to peripheral. Okay? Input, receive data from peripheral and send data to computer. So that is the connection of the output and the input. So receive control signals from computer, send control signals to peripheral, receive addresses from computer, so either port number to identify the peripheral, okay, assuming that you have different computers and then you want to connect, then there's different port numbers, it's possible. So interrupt signals, okay, it can send interrupt signals. Next is the CPU connection. The CPU connection is able to read instructions and data, writes out data, sends control signals to other units, and receives interrupts. Next is the buses. So there are a number of possible interconnection systems. Single and multiple bus structures are most common. So example, we have the control, we have the address, we have the data bus, and or you have the unibus. So what is a bus? So this is a communication pathway connecting two or more devices, usually broadcast, often group. So this is a number of channels in one bus. It could be a 32-bit data bus, okay, which is 32 separate single-bit channels. So power lines may not be shown. So what is data bus? Data bus carries data. So remember that there is no difference between data and instruction at this level, with this a key determinant of performance. So either 8-bit, 16-bit, 32-bit, or 64-bit. Next is the address bus. The address bus identifies the source or destination of data. Example, the CPU needs to read an instruction from a given location in memory. So the bus width determines maximum memory capacity of system. So for example, the Intel 8080 microprocessor has 16-bit address bus giving 64K address space. Next is control bus. Control and timing information, memory read or write signal, interrupt request, clock signals. So this is an example of bus interconnection scheme. So we have the CPU, we have the memory, and then we have the I/O. So the CPU have control lines. So the CPU also have the memory, also the I/O have address lines, and we have the data lines that connect the CPU, the memory, and the I/O. So this is the bus interconnection. So what do buses look like? A parallel line on circuit board. So these are ribbon cable, strip connectors on motherboards, example PCI, or sets of wires. So this is the bus. So this is a physical realization of bus architecture. So as you can see here, the arrow identifies the buses that holds the CPU, the memory, and the I/O boards. So single bus problems. Lots of devices on one bus leads to propagation delays. Okay, so most systems use multiple buses to overcome these problems. So this is traditional, okay, with cache. So we have the local bus here, we have the system bus, and we have the expansion bus. Okay, so the local bus controls the processor and then the local controller and the cache. Okay, it connects them, the three. And then the system bus handles the local bus and the main memory, while the expansion bus controls the connects the system bus with the expansion bus interface with the network, SCSI, modem, and serial. So this one is the high performance bus. Okay, so that's how it looks like if you're going to perform the high performance bus. We have the system bus, we have the high speed, and we have the expansion bus that interconnects every single objects here. We have the graphic, we have the video, we have the LAN, okay, we have the modem, we have the serial, we have the main memory. So bus types, we have the dedicated, separate data and address line, multiplex, we have the shared lines, address valid or data valid control line, advantage or fewer lines, disadvantage, more complex control, and ultimate performance. Bus arbitration. So more than one module controlling the bus. Example, the CPU. Only one module may control bus at one time, and arbitration may be centralized or distributed. So when you say centralized or distributed, when you say centralized, single hardware device controlling the bus access. Okay, it may be part of the CPU or separate. Distributed, each module may claim the bus, okay, or control logic on all modules. Next, timing. Coordination of events on bus. It could be synchronous, okay, events determined by clock signals. Control bus includes clock line. Okay, a single 1 to 0 is a bus cycle. All devices can read clock line. Usually sync on leading edge. Usually a single cycle for an event. So this is a sample of the synchronous timing diagram. Okay, we have the status signal, we have the stable address, the valid data in and out, wherein it will show the clock, status lines, address line, okay, the read cycle and the write cycle. So read, we have data lines and read. The write, we have the data lines and write. So this one is the asynchronous timing read diagram. So we have the, of course, we have the status signals, we have the stable address, and we have the valid data that handles the status line, the address line, and the read line and data line. So this one is the asynchronous timing write diagram. So we again, we have the status line and status signal. We have the address line and stable address. We have the data lines which writes, okay, and the valid data. So PCI bus. So when you say PCI, it means peripheral component interconnection. So Intel released to public domain, it could be 32 or 64-bit, which composes of 50 lines. So PCI bus lines, so we have the system line, we have the address and data, we have the interface control, we have the arbitration, and the error lines. When you say system lines, it includes clock and reset. Address and data, 32 time max lines for address data. So interrupt and validate lines. Interface control, so we have the arbitration, not shared, direct connection to PCI Bus Arbiter. So this one are optional from the PCI bus line. We have the interrupt lines, we have the cache support, we have the 64-bit bus extension, and we have the boundary scan. PCI commands. So this is the transaction between initiator and the target. So master claims bus determine types of transaction, either input, output, read, or write. We have the address space and we have one or more data phases. So this is an example of the PCI read timing diagram as shown on the screen. Okay, we have the clock, we have the address, we have the data, we have the bus, we have the bytes enabled. Okay, we have the data transfer here, and then showing whatever, if ever it will wait or will transfer data, or the phase of the transferring. So this is the illustration of the PCI Bus Arbiter. Okay, so we have the PCI devices and the PCI Arbiter that shows the connection between the boxes. Okay, so this is the PCI Bus Arbitration. This is the sample.